Alright, so in this video we're gonna talk about um, transform of Fourier. So that's the theory video about it. So I just want to state that I'm not necessarily gonna go through all the theorems and all the details about Fourier transform. Like the process I go through to make these videos, I just pick up all the exercise, I collect them, and then I solve all of them related to the thing that I'm gonna record the theory video about. And then I just solve them, and then I just analyze all the theorems and concepts that I've used to solve them, and then that's what I'm gonna present here. So there are a lot of concepts that I'm not necessarily gonna talk about. So as international students, we don't really have the time to go through all the theorems and all the formulas and all that. So the point here is being very precise and focused on the exercise. Okay, so the first topic here is the Fourier transform. So what is it? Basically, you have a function and then you want to change the domain. So you're gonna go from x to t or t to x or whatever variable you choose. So in order to do that, first of all, you need to be sure that the function that you want to transform is inside the space of L1 of the real numbers. So the theory to prove that your function is inside this space is you're gonna integrate, considering the real numbers, the modulus of your function, and then you're gonna reach a result, and this result gotta be less than plus infinite. Also, it can't diverge basically. So that's it. Here I wanna state a very little remark. I guess in the exercise 2, you're probably gonna watch the exercise 1 after this video and then exercise 2. So in exercise 2, I've proved that our function belongs to L1 by integrating the function dx and proving that it is less than plus infinite. That's wrong because I need to integrate the modulus of our function. But the thing is, most exercises work with positive exponentials. So something like exponential of minus a modulus of x, something like that. So those functions, they're always positive. So it doesn't matter if you're integrating the function itself or the modulus of your function, because it is always positive. So that's kind of automatic in my brain. So when I was solving the question, I just disconsidered the modulus, and that's not right since the function is cosine of theta. So cosine of theta can be negative. It depends on the value of theta. So that's an error. And I'm just, because the video is 40, 50 minutes, I don't know how long. So I'm not recording it again. So I'm just stating a little mistake that I've done. And well, but that doesn't change the rest of the video, since I'm just proving that our function belongs to L1 in order to follow to do the Fourier transform and all that goes after that. So yeah, I think that I've reached the value 0 of the integral, and if I was using the modulus, that the right solving, I would be having pi as a result. So both are less than plus infinite, so both ways it belongs to L1, so it doesn't really matter, okay? But that's a little mistake that I wanted to state, okay? So exercise 2, I've done that little mistake, so pay attention on that. All right, so once you've proved that your function belongs to L1, now you can do the Fourier transform. So for all values of x belonging to the real numbers, uh, the f of x, that's a little hat, it indicates that it's the function transformed. The formula is equal to the integration, considering the real numbers, of your function times the exponential of minus 2 pi I x t dt. So here you're considering x as a constant, so that's why it is appearing at the final result, and you're integrating in t, since your function here that you want to transform, the domain of it is t, okay? So that's just the formula that you're using. The exercise is going to give you the function, and you're going to transform it like that after you prove that it belongs to L1. So since you can transform a function, you can do the opposite. So if you have a transformed function, you can reach to the original function by doing the inversion of the Fourier transform. So the formula of it is kind of the same. So you're integrating in the real numbers, but here is not your function f of t. Here is your transformed function, since you want to invert it, and you're multiplying it by the exponential of 2 pi itx. So here you gotta know that it is positive. Here at the Fourier transform, it is negative. So that's a little difference. And also, here you consider t as a constant, and you're integrating an x, since your transformed function consider the domain x. Okay, so that's basically it. Here I'm not really proving this here, but I've just drawn the box around. But you gotta notice, because in exercise 1, I guess, one of the items is to prove this. So that's why I'm not proving it here. You're gonna try to do it later. So in a lot of exercises, you have a function, then you do the Fourier transform, then you reach the f hat. That's the first Fourier transform, and then you want to go back to your original function, but instead of using here the integration to do the inversion, what you do is you're going to transform it again. So you'll have an f with a double hat, and then you reach f of minus the variable, minus the original variable. So here minus t. But probably your function that you're going to have in your question is a pair function. So it doesn't matter if you're reaching f of minus t, that's actually equal to f of t. So instead of doing the inversion by the integration, you can just transform it again and you'll reach the same function. Okay, so that's an idea that a lot of questions explore. So that's it about the Fourier transform. So here we have the convolution. That's basically, if you have a function f being convoluted with a function g, that's the formula. So integration of the real numbers of f of x minus t gt dt. That's the formula of if you do a convolution product. And well, what it is important in order to solve exercises, I guess, is basically two things. First thing is to know this general formula, because you'll need to be able to identify if that's a convolution product. Like, let's suppose that instead of fg here, you just have this integral equals a p of x. Let's suppose you only have that. You need to look at this integral and be like, okay, that's a convolution product. I can write it as this. So you need to be able to do this, to visualize, okay? That's the first thing. And the second thing is, if you use Fourier transform on a convolution product, you'll have the Fourier transform of f times the Fourier transform of g, okay? So in the context of questions, you'll probably have an equation like that. You'll need to visualize that you have this kind of equation by knowing the convolution product. So you will write the equation as this, and then you're gonna apply the Fourier transform in the equation. So you'll have P transformed equals F transformed times G transformed. So that's the process of solving the question. You'll know it better when you're doing the exercise. But about convolution is knowing how to visualize and knowing that the Fourier transform of a convolution product is the transform Fourier of f times the transform of Fourier of g. Okay. Now we have the Riemann-Lebesgue theorem. So what it states is, if your x is going to infinite, and your transformed function while this x goes to infinite goes as well to infinite, so it diverges. That means that your original function without the hat does not belong to L1. And that's all we can state. Okay, so let's suppose you have in your question f hat of x, so the function transform. And let's suppose you tend your x to plus infinite, okay? And let's suppose that your transformed function it goes to 0. Okay, let's suppose this. All right. So you can't, by what you've done here, you can't say that your f of x then belongs to L1. You can't say that. Okay, you can only analyze and affirm this. If your x goes to infinite and then your transformed of Fourier of your function goes to infinite, so it diverges, then your original function does not belong to L1. You can't say the opposite. Okay, so if you tend your x to plus infinite and then your transformed of Fourier of your function goes to any value that's not infinite, then you can't state that your original function belongs to L1. You can't say that. Okay, so that's the state of Riemann-Lebesgue. And our last thing here is the Fourier transform. It is stable by derivation. It means that you can derive a function that is transformed by Fourier. And in this context, you're going to use in a lot of exercises this formula here. So let's suppose you have f 2 times derivated, the transformed of your function 2 times derivated. Okay, so this appears on an equation that you're developing. Okay, but you don't know the value of this. Then you're going to use this formula to write down as 2 pi times I pi x to the power of 2. Okay, since here that's the number of derivations that you've done to your function, and here that's in the power to pi x. Okay, so squared times your function transformed without any derivation. And this value you're probably gonna have in the context of the exercise, okay? So it's basically you're writing down the transform de Fourier of your function derivative in a way that you know the values of it, okay? So you have this, but you don't have this. So in the context of the exercise, you'll be able to write it like this, okay? And find any values, any results that the question is asking for. So that's basically it. That's all the concepts that I've used to solve the questions. Once again, this is very, very precise if you're at Centrale, and I guess this will help if you're at any other university in France, but it is very accurate to Centralion. Okay, that's it.